This meeting is being recorded.
In this next example, we'll take a look at sample exercise 5. And just like in sample exercise 4, we're given a data table with 3 different experiments listed here and the concentrations at which these experiments were performed. So we're looking here to see this reaction of nitric oxide with hydrogen gas. And we're given the data, again, the concentrations, and then over here on the right, the initial rates for these reactions. So we're asked in part A here to determine the rate law for this reaction. So if you recall, a rate law has this general form where the rate is equal to some constant K, and then we're going to show the relationship to the exponent here being the order of nitric oxide and that of H2 gas. So we're going to solve for these two exponents here, M and N, and if you recall, we need to hold one concentration constant and change the other. So if we wanted to solve for the order with respect to H2 gas, we could relate reaction 2. We could put reaction 2 on top of reaction 1. We could divide by the rate, so 2.46 times 10 to the negative third molar per second. So this is reaction 2, and then reaction 1 on the bottom, that's 1.23 times 10 to the negative 3, same units, and this will be equal to the same rate constant. And again, we're going to hold nitric here constant. So these will cancel out along with our K values. And then we see that we have our concentration over here for our H2 gas. So if we were to simplify this equation here, we would see that 2 would equal 2 raised to the n power. And we would see that the only exponent that would satisfy this equation and give a true statement would be if n was equal to 1. So this is a first order relationship. Let's take a look at what equations we could use to solve for the order with respect to nitric oxide. If we were to take reaction 3 and compare it to reaction 1, for example, we could, because we're changing nitric there, but then we would be holding the H2 constant. So we know our Ks will cancel out. Let's compare reaction 3 to reaction 1 here for nitric. And then we don't need to write H2 because we know 0.1 divided by 0.1 will cancel out as well. But we can write the rate for reaction 3 here and divide by the rate for reaction 1. So the exponents are the same. So this is really showing us 4 is equal to 2 to the m power, where m would have to be 2. So this relationship is now second order. So overall, we end up with a rate law that would look like this. The rate is equal to NO squared and H2 to the first power. So this is our rate law that we can use to calculate the rate constant in this next part of this calculation here. So we're just going to take some data from any one of these experiments. So let's use experiment 1. That shows the rate is 1.23 times 10 to the negative 3 molar per second. And then we're going to solve for K. So we're going to plug in our concentration of NO and our concentration of H2 gas, making sure to square the NO value here. So if we were to rearrange this equation and then divide by 0.1 squared times 0.1 down here, we would see that our K would be equal to, remember our units, molar squared and molar. So this would cancel with this, and our units will end up being molar to the negative 2, seconds to the negative 1, and this would initially give us 1.23, but due to my significant figures, these are only 2 values here, I'm going to have 1.2 molar -2, second -1 as my final K value. And I can carry this through and use this in my last part of this calculation, where I'm asked to calculate a new rate when my concentration of NO is 0.05 and H2 is 0.15 molar. So to solve for rate, we'll plug in our K, so 1.2, and that was molar -2, second -1 were my units, and then my concentration will be 0.050 molar squared times 0.150 molar here. So the molar squared will cancel. My units will end up being molar per second, and I just have to make sure to square this value, but 1.2 times 0.05 squared times 0.150 will give me a rate equal to 4.5 times 10 to the -4 molar per second.